Good morning, everyone. Today is March 25th, and this is the John Chappell Natural Philosophy Science Chat. Now, we don't have any particular topics this morning, so I had suggested a few topics, but I want to see whether there's any topics out there in the audience that you might want to talk about. And another thing I wanted to share today is that they have announced the conference, the CNPS conference. Let me see if I can share it. So that's going to be at the University of British Columbia from July 19th to the 22nd in Vancouver, Canada. So actually not very far from me here in Seattle. So I hope you all consider going to that conference. I've been to it before, and it's pretty interesting. And you can present a paper or have it published in their proceedings. So that will be coming right up before you know it. Okay. Now let me get back to control here. Okay. So I had a few topics in mind. Did anyone else have any topics they'd like to start out with? If not, then...
Okay, Franklin.
Yes.
Can you hear me?
Yes, Peter, I can hear you.
Yes. If we have a little time, I want a few minutes continue with where we ended at the last week video conference. Yes? Can I? So there was a question last week that there is no contraction in Einstein's special theory of relativity, and there were some objections, maybe also from your side. So I want to add to this that in Einstein's 1905 paper, there really is no length contraction. All calculation or relation which is in paper 1905 means the difference in measurements on length from position of various frames, and it doesn't mean anything real in physical action. That means in 1905 paper, all physical realities of lengths in all reference frames remains the same, and the relativity in this paper means that to find a relation for transition of our measurement, what we do from one reference frame and how we see it in another reference frame. So there's no physical changing, so no length contraction exists there. The length contraction, what is called in paper 1905, means what is your change of measurement of length of some moving object, and the task of relativity is to bring a relation to recalculate your mistakes. Yes, this is the one thing which was not clear what I told last time.
So you are saying that in Einstein's 1905 paper, there is no length contraction. Is that correct?
Not physical length contraction. Length contraction, what is called there, means your change of your measurement of some moving objects. If the objects are not changing, or the lengths, the physical lengths or physical bodies are not changing.
So if length contraction didn't come from the 1905 paper, then where do you think it came from?
I can say, I will read you a sentence of Einstein's paper. Exactly. One moment. We have to add that in fact all relative Einstein's after 1905 papers there was some reaction of physicists, and he saw, as in many times, he didn't come to his ideas or to his equations. He simply always react to situation what was happened around him, and in fact, his special relativity is formed in paper 907, which I also mentioned last time. And in this paper in 907 he explains, I will find it, one moment. So I will read something from this paper. Yes, I quoted the Einstein's from 1907 paper.
1907, not the 1907.
1907, and title is on the relativity principle and the conclusion drawn from it. This is paper in which Einstein drew the conclusions from his 905 paper. So the title of the 60 pages paper from 907, Einstein's paper, it has 60 pages, and the title is on the relativity principle and the conclusion drawn from it. And in this paper, he says, Michelson-Morley experiment contradiction was removed by Lorentz and Fitzgerald's ad hoc postulate of certain contraction of moving bodies as artificial means of saving the theories. Surprisingly, it turned out that a sufficiently sharpened new conception of time was all that was needed to overcome the contradiction. The conception of luminiferous ether does not fit into this conception. Therefore, Lorentz-Fitzgerald theory should be abandoned. Yes. So it was, in fact, the special relativity was adverse solution to the proposed Lorentz-Fitzgerald solution, where the length are contracted, and by this way the Michelson-Morley experiment is explained. I am trying to find the exact sentence where he is in his 1907 paper, 60 pages paper, says exactly what he meant, or what he thinks it is in 1905. There is exact sentence. I will find it. So please, claim another thing, claim another person. I will find it.
Peter,
Okay.
go to the section where he talks about geometric length. You have to go in a couple of sections where he talks about geometric versus the different kinds of length. Are you familiar with that?
Harry, go on and talk something. I will find exactly the sentence from 1907 paper to clarify it. Yes, so give me 1-2 minutes, please.
How many papers did he come up with in 1907?
So you see, it's absolutely so. As for instance, about the general theory of relativity, he wrote 15 papers about it in 4 years, from 1911 to 1950. He wrote 15 papers. Each paper was contradict, and all physicists was writing in that this is wrong, that is wrong, that is wrong, and he always repaired his equation and his papers, and so I'm sorry, I will find it.
Well, I'm just trying to look it up on the internet here, and it's like apparently there are a couple 1905 papers. So if you could say what the title was, the actual title was, then we could take a look at it. There's apparently comprehensive essays on relativity 1, 2, and 3 in 1907. So that could be quite a few possibilities. Although
I want the title of paper from 1907 is on the relativity principle and the conclusion drawn from it. Is the title of this paper, 907.
let's see, there's quite a bit of noise coming out of somewhere here. Let's see here. Let's mute Jan here. I think that's where the noise is coming from. Now, recently in the email threads, people like Ronald Hatch are arguing very passionately that length contraction actually does occur.
Of course, but I don't disagree with this because, but it is, I am saying about the time, about the special theory relativity, but later, 4 years later, he fully accepted accepted the length contraction as a reality. It is in 1911 paper. Uh, he's writing exactly that. The length contraction is physical reality. This guy, if you, I can say this because I am now preparing a paper exactly about these things. I go through this Einstein's paper in last year, and it's really funny. It's really funny what you can find in his contradiction in all his 20 years careers. He in fact proclaimed always two opposite claim as valid. So he in special theory relativity he is definitely saying that the length contraction that the length in all frames are the same, but three is afterwards. He's speaking standardly as the law as the. I have here one. For instance, one quarter. By means of Lorentz transformation, the rigid rod is shortened in motion. If we have based our consideration on Galilean transformation, we shouldn't have obtained the contraction.
Here it is here.
It looks like Harry's got the paper there.
Yeah, but unfortunately, it's not on the internet. But it's confusing what he says here. He says here on page just before part 3, says, it is clear that observers who are at rest relative to a reference system S can ascertain only the kinematic with respect to S of a body that is in motion relative to S, but not its geometric shape. So that would lead me to think that there is no length contraction because it doesn't change the geometric shape. It just changes what the appearance is, not the actual shape itself.
So that's what Einstein's saying, because it's always, from what I've been able to see, length contraction looks like an optical effect and not a real effect, even by Einstein's
well,
words
some people,
himself.
this is really what the issue is. The issue is that there are different
So
interpretations.
I have a quote from a 1905 paper. Yes, so in 1905 paper, here is in accordance with the principle of relativity, the length of the rod in the moving system must be equal to the length of the stationary rod.
Well,
Yes.
that seems pretty clear that he's saying that the length of the rod doesn't change. I don't think he could be any clearer than that.
Of course. It is
Right.
clear what he mean there, that in accordance with the principle, well, the length of the rod in the moving system must be equal to the length of the stationary rod. But
I think.
But what I don't get is that if Einstein said that, and that seems pretty clear to me, then how is it on all these explanations of relativity we have the picture of the rocket that's being compressed?
I think it would be clear that is my mic working?
Yes, your mic is working. Go ahead, Gord.
Okay. Sorry, I was just trying a new computer. I think it'd be kind of clear what Harry says. It's kind of ambiguous because there again, in that statement, he doesn't say, what instruments he's using to measure the rod in each environment. Is it the instruments that are in the same environment, same frame as the rod, or is it the instruments, in one frame or a totally separate frame is being used to measure each rod? And so there is ambiguity in what the statement is. There's missing information there.
of course, if you are on this position, we must definitely start because we must definitely start from the length contraction, and this is the base, because now what you told is just believing of anybody of us. If the explanation is so or so, but definitely in his works we can find it is full of contradiction and full simultaneous claim of reality, and so. I think the best thing is to, if you want to discuss, is to discuss the time via dilation, and because it is the basic, the time is the base for which the special theory relativity and general theory relativity must to be at the beginning rejected, because time is not a physical that you have a space populated with clock. If you read the Einstein's paper, where he talked that where he on one page explains how the clocks are placed in the space. So it's absolutely funny. He's talking about nothing like some time which is flows or spawns on some places is absolute nonsense. And from the relativity special and general has to be rejected from the beginning because of his absolutely not understanding of time. This is before 1905. Never do nothing with time, and he in fact replaced all problems which we have. He replaced it with the manipulation in time, as I told the last time, time and movement and time and velocity, it is the same notions, and and we must react to the speaking and talking about the time. We must speaking about the space and velocities and gradient of fields and acceleration. That is what all physics is about. And all other, everybody who didn't do not do this and do not from the beginning reject the relativity as special as general, because the absolute not understanding of Einstein of time, he will be trapped in a cyclic from which there is no go out, because you cannot separate velocity from time, And in fact, in conclusion, also the length from time, it is inseparable. And for the last 300 or 400 years, the unit of time and unit of velocity is fixed. And if you change the time, you've changed a basic comparative velocity. So your physics splits and it is crashed. You are not talking about no physics if you don't understand that you have the base of physics. The physics is based for last 400 years on the principle that by unit time you define the unit velocity. 1 meter per second. It is your unit. You measure it.
Well, what exactly is your bottom line here, Peter? Now, from listening to you, it seems that you're saying that Einstein himself doesn't appear to believe in length contraction. Is that your bottom line?
It doesn't matter if we are talking about he one time he's speaking that it is called, but it is the same as with ether. he beginning. I can quote you about the ether at the beginning in 1905. He reacted the ether and I find another paper from 1924, which is absolutely not known also between dissidents. And in paper 1924 he listen this.
Well, Peter,
I quoted from this paper. Listen this. The mechanical ether designed by Newton as absolute space must therefore be considered by us as a physical reality. Just listen to this sentence. Another sentence. In Newton's theory of motion, space has physical reality in contrast to the case of geometry and kinematics. Another sentence. General theory of relativity add characteristics to the ether that are variable from point to point and determine the metric and the dynamic behavior of matters. So I will in my paper, I'm preparing this paper from we usually or standard renew the Einstein's paper from 1920 from that conference held in Leiden, but it is more serious paper from 1924 where he absolutely returns that we became a more enthusiastic advocate of existence of ether than the all subtotals of ether before 1905. So it is.
All right.
This is all Einstein's relativity. He 1 year he said this, and I see in 1924 paper he said he's absolutely back. He says that Newton's space must be considered as a physical reality. It's unbelievable, and it is in
Okay.
all
All right,
this.
Peter. So is your main point then that Einstein is basically contradicting himself all the time, depending on
All
which?
the time, and in all cases, and he's. You will see. Now I'm doing this paper, and it's really funny. It's really
Okay.
funny.
All right. Well, thank you, Peter. I'm just wondering, does anyone else have any comments on this subject before we move on? Okay, so that was Peter and length contraction. So it seems that, we
Well,
could
I'd like to comment just a little bit. I went through this whole issue and looked at a lot of different books, and essentially what it boils down to is that there isn't really about whether length contraction is real or not real, and that seems to be it depends on what physics book you look at. Might depend on what particular interpretation of Einstein's theory was popular at a particular time the physics book was written. So there really isn't any resolution of this that I could see by going to any physics books or reading Einstein's papers. It's just, some people say it's real and some people say it's not. So that's about all you could get out of it.
I mean, looking at some of the reference and some of the discussions, some people are saying things like the Michelson-Morley experiment proves that length contraction is true because that's the only way it could have come out with a null result. Although I'm not convinced of that. I mean, because it could simply be that the ether is entrained and that is the result of the null result. And since they can't exclude that, they really can't say that the reason for the result is that, you know, one side of the interferometer contracted. So I'm not terribly convinced that I've seen any physical experiments that will actually show the length contraction. I mean, I suppose if they like did something where they showed me a photograph of a rod that was stationary against a stationary background and then took a picture of the same rod moving at high speed and it was shorter, then maybe I might be convinced that there's something to this length contraction thing. But I've never seen any experiment like that. Nothing even close. So I remain highly skeptical about whether length contraction is just basically an optical effect and not a real effect.
Frankly, most funny is that why we are always going back to 1889 Michelson-Morley experiment, when after that 30 years continue these experiments and for instance, you knew the Miller names or so, but Miller in around 10 years from 1922, 25 to 1923, who published in all top ranked journals in Nature, in Physical Review, in Science. The papers, for instance, the title was The Absolute Motion of the Solar System and the Orbital Motion of the Earth determined by the Ether Drift Experiments. It was in 1934 in Nature published. And but why the relativist is always going back? Of course, we all knew this, the Sagan experiments, or I'm sorry, Sagnac experiments, but it finished it. In fact, Miller in his paper documented at a drift velocity in the average of 20 kilometers per second, among other things. So, but it is the same in general relativity. The mainstream is always going back to 1915 papers. They are fixedly stay on. Einstein
Yes,
himself.
well, unfortunately, we could go on and talking about relativity forever. I think Harry characterizes it that it's irksome and that one could go round and round and round and never really discover or find out anything. So, so thank you for your question, Peter, but I think it's time for us to move on to another topic. So I had my list of topics that I was proposing for this talk. So, and one of them had to do with neutrinos. So this came out of my own research on neutrinos. Now, neutrinos is big science. I mean, there are several, you know, multi-million-dollar experiments that have been built. I mean, huge experiments to detect neutrinos, like the Super Kamari experiment in Japan. If you've ever seen it, is like in an underground, you build like this gigantic pool, this huge cylinder, which is like, I don't know, like 50 feet wide and like 100 feet tall or something like that. And then surrounded by the most ultra sensitive light sensors ever created by man. And you fill this up with the purest water possible. And you think that that kind of experiment wouldn't even be able to get done. But yet they've done that. And they've been able to detect what they think are neutrinos. And then they've got like this ice cube experiment where they're drilling holes in the Arctic ice and they're dropping these sensors down in the ice to see these neutrinos coming in and detecting them, which is also pretty incredible. So it's pretty big science. It's like the LHC. Millions of dollars have gone into detecting these neutrinos, which are apparently streaming through us all the time.
Franklin, the principle was absolutely wrong because neutrino is some particle with mass about minus 10 to minus 40 or 42, somewhere there. And they are trying to detect neutrino for 20 years before, so that they are waiting that this small particle will make a transition of electron, which then which emits a photon. It's absolutely nonsense. The neutrino has not such enough energy to make a transition of in atom of electron so that electron could emit the photon. This is the standard in radioactivity or all measurements which we have, but it is nonsense. We are saying that the neutrinos doesn't react with matter, but it is nonsense. The neutrinos react with matter, but they have not enough energy to make a transition to emission of photon, and they are looking with photomultiplier, writing it must be changed. Another
Well,
progress.
the thing is that, I mean, you're saying that on a theoretical basis, but from a empirical measured experiment basis, you know, there is something being measured in these experiments. So they get a direction and they get an energy, and if they think it's coming from the sun, it comes from the opposite side of the earth. So, I mean, what are you arguing? Because, I mean, certainly these experiments are measuring something. So you can't say that no matter what you have on a theoretical basis, that it can't happen, because it is happening. They're measuring something. So what are they measuring if it's not a neutrino?
Yeah, of course, fluctuation could happen, but principally these experiments are wrong. Neutrinos are interacting with mass in very great measure, but they are not able to produce a photon. So we must make a calorimetric measurement.
So, well, the question is, then what are they measuring?
Please.
What are they measuring in these gigantic neutrino experiments if it's not neutrinos?
Photons transition and waiting. If happens something, then one neutrino of billions or billion neutrino will have such an energy that is able to produce a transition of electrons and photon emission from that. So it is absolutely stupid. Neutrino is interacting with mass with very great matter, but it has to be measured with, for instance, calorimetric methods or something, another methods than to waiting on excitation of electron and producing and emitting photons, which they are able to catch with photomultipliers or so. That's all from my side. What is concerning the neutrino.
Well, that still doesn't, you know, answer my question of these neutrino detectors based on these photomultiplier tubes are catching something.
Yes, they are catching photon. If atom emits photon, so multiplier is catch the photons. It multiplied it because one photon we are not able to present, so it or to detect. There is a multiplying process that if one photon is
So did they catch a neutrino, or are you just saying that those things are noise?
I am not saying that is noise, but maybe statistically it could happen that one neutrinos or that more neutrinos are joined together and make this excitation. But I think that principally it's absolutely wrong. You see.
Well, it's like this is one thing I think is strange about neutrino science, is that how can you say anything about a neutrino when you have basically no idea what on earth that thing is, right? So how can you?
That's the thing. Now you know how we can say neutrino. We of course we never can detect, but we have a decay processes from the neutron. When the neutron decays, it decays to one photon and one electron, and the momentums are not enough when you calculate the momentums of photons and electron, which decays from neutron. So you you can say for sure that there is also another particle which we never saw it, we never measured it, but when we calculate the direction of this product, for instance, of neutron, yeah, let you take a neutron decays to electron and some gamma, standardly. And when you calculate the momentum of this gamma and the electron and mainly the direction, you recognize that something is missing, and this missing.
Well, Peter, let me ask you this question: do you think neutrons exist? I mean, neutrinos exist? True
No,
or false?
of course, something exists because, in fact, neutrino is the basic substance of ether. So, if it is not directly the ether, so it is the basic core of basic excitation of ether. It is the.
So you're saying that neutrinos basically make up the ether. Is that what you're trying to say?
But I am sure about that for sure neutrino you couldn't imagine it like a point, like a particle. It could be some fluid. It could be anything. You know, nobody has no idea. Something means that it is some string or something like this. But the current problem is that we are okay. That's my opinion.
I think they're still trying to discover what the properties of a neutrino are. I mean, they know there's the energy and reaction that causes interactions that cause the photon to be emitted from an atom, but the neutrino itself is not multiplied by the photon two multiplier tubes. What's multiplied is the reaction that's created by the neutrino striking an atom, which creates the photon. And so that's how they're sensing that. And that's what happens with that in Japan. That's what happened with Ray Davis's experiment. And I actually live 30 miles away from where neutrinos were first confirmed to be in existence in the gold mine in Lead, Deadwood. And Ray Davis had a large vat of cleaning fluid, if you will, even. I can't recall the term of the actual matter at the time, but he was the one that first discovered and measured neutrinos from the sun. He only discovered 1/3 of what they expected to be coming from the sun based on calculations. And later they found out that they believe neutrinos come in 3 different types of neutrinos. And let's see, I think the electron, proton, and neutron neutrino. And that's what the one in Japan finally detected the other 2 types. And when they did that, it came out to be the amount of neutrinos they expected to be coming from the sun was what they detected. Now they're still trying to determine what the properties of a neutrino are. Originally, they thought a neutrino was massless. Now, because there are 3, not just because there are 3 different types of neutrinos, but what they find unusual, what they can't explain yet, and they're trying to discover with new experiments here and lead experiments around the world, is a situation where one type of neutrino they know is emitted, and when it reaches the detector, it's a different one of the 3 neutrinos. So it's actually changed the type of neutrino or the characteristic of the neutrino they're receiving. And so they call it neutron oscillations or neutrino oscillations. They're currently trying to do an experiment in association with probably elsewhere in the world too, but they're doing it here in the Sanford lab, which is the underground gold mine where in the exact same area where Ray Davis originally discovered neutrinos. And they're trying to do an experiment by shooting a beam of neutrinos, which they are creating a beam of neutrinos then at Fermilab in Chicago, Illinois, shooting that beam through the Earth because the neutrinos can penetrate the Earth, as you mentioned, Franklin, because I have actually seen pictures of the sun taken by the neutrino detectors down in Ice Cube in the Antarctica, and they were shown to me by a professor who actually had one of the neutrino detectors that they drilled down into the hole, here in the college in Rapid City, South Dakota. And they have, you can see that there are pictures of the sun taken from the opposite side of the Earth based on neutrinos. I don't know all the details of that by any means. I know what I've been shown, and I know very little about actual neutrinos. But what they're trying to do with this Fermilab experiment is detect if they do in fact change what they call flavors from one over distance. They're trying to determine at what rate or what distance they travel before they make that transition. But because they do make a transition from one type to the other, they are now summarizing that they do have a very tiny mass. And that's about the extent of what I really know of neutrinos. I've talked to some of the professors down here, and they're coming from around the world to help with this experiment. There's probably like 200 different physicists that come here and are involved in this experiment. And I'm sure that there's just as many as at the other sites. But what they've explained, personally, I've talked to them too, and they say it's like a combination of three wavelengths of super short light, and because the wavelengths are all different and yet they're traveling together, it's basically kind of like a beat frequency between the three wavelengths. But also between those three wavelengths traveling together, they do appear to, at points in time at least, have mass. And while they're in that condition, they will change to a different pattern and move on. Beyond that, it's all, they're still trying to discover it. So I'm not going to make any speculation exactly what neutrinos are. I believe everything is a wave pattern of one type or another, but exactly what that pattern might be in the case of a neutrino, I haven't even begun to speculate, and I think they're still trying to find it out. So I believe they're certainly there, but what they are, they're still trying to discover. And that's all I got to say on the subject right now.
Yeah, you touched on several interesting things. I think one of the more interesting things is that they think that neutrinos, there are three types of them. So I think that's based on the type of electron. So it's like electron, muon, and tau to correspond to the electron, the type of electron that gets kicked out in the interaction. Of course, my question is that how did they know that, say they only saw 1/3 of the expected neutrinos? How is it they did what? Maybe the problem was that their detector that they had simply wasn't sensitive enough to detect the other 2/3.
That's exactly it. That's what Ray Davis's experiment only detected 1/3 because of the type of receiver he was using. And that's what the receiver in Japan solved. It solved it by having a different type of receiver, and that receiver did detect all three types. So that's exactly it.
Well, maybe there aren't three types. Maybe there's just three ways that neutrinos interact with matter in the detector. And because that's always kind of been when you try and figure out, well, what isn't neutrino itself, it seems highly unlikely that neutrinos can turn into different things while they're in flight. There's be much more attractive if neutrinos were just basically one thing and not, say, three things.
Well,
no, I'm still doubting the basic tenet that these are fundamentally different things.
Well, like I said, they're just speculating at this point, and one of the descriptions is three wave patterns traveling together, and as they combine differently, you get, anytime you get different frequencies of waves moving together, you will get points where they will add to each other and points where they will subtract from each other, and you'll get a different characteristic amplitude as they move along and go over distance. And that's the characteristic they're summarizing, that something like that happens with neutrinos. It's not just a single wave, but it is multiple waves of different lengths that are beating against each other. And like I said, at different distances, you're going to get additive and subtractive characteristics. Exactly how they detect the differences between the three neutrino types, I have no clue. I only surmise that they must realize what type of reaction causes what type of neutrino. So if they are emitting one type and they receive another type, then they can only suggest to themselves that it's not the type of receiver that they're using, but rather that something changed in the process of transitioning from one location to the other to change the characteristics of that neutrino. And that's the way that they're looking at it. They know what they expect to be transmitting one type and receiving that same type, and it turns out that what they're transmitting is not what they're receiving. So if it was the material, then that wouldn't be the case.
Well, my own personal feeling is that the neutrino is like a photon in that it's electromagnetic in nature, and that would explain why the neutrinos arrive basically the same time as light, because they are basically the same thing. My hypothesis is that the only difference is that a neutrino is the very, very smallest possible electromagnetic wave packet you can possibly have, due to the quantization of space. So
I think that's probably a good summarization.
No, I would say that.
I agree with you. It's probably the smallest or one of the shorter wavelengths. And when you consider that the source of a neutrino is due to the nucleus, a reaction in the nucleus, and not like a photon, the reaction of the lower level energies to becoming higher level energies of electron patterns, then it makes sense that they would be much stronger, much shorter wavelengths. Because of their source where they're coming from is the nucleus, not the orbital atoms or electrons.
Yeah, so it was a little bit like we were discussing with photons, that we think that it's like a shock wave, except now normally when you generate photons, you generate like lots of them, and they come in like a whole stream of them. But these neutrinos seem to be particular point events. I would liken it to like if you have a Newton's cradle and you drop the ball down on one end, and energy travels through the other three balls, and then it kicks out the other ball at the end, but you never see anything going on in the middle because it's just a singular shock wave going through the system. So I kind of see neutrinos that way, although if a neutrino...
I think the thing you're saying that neutrinos are only emitted occasionally, but they're emitted all the time. The problem is that they go through everything, and like I said, through your fingernail, there's billions of them going through your fingernail all the time. So it's not any different in light in that respect. It's just that they don't react with anything, so we don't sense their existence, that they're there. But there is just as many neutrinos as there are photons.
Yeah, I got into this because there was here in Seattle, we have the nearby University of Washington, and every once in a while they have people give talks and seminars, and as a member of the public, I could show up there and actually send messages to the people who are doing that. So there is this person called, let me see if I can bring the email here, because this is one thing that even as alternate scientists, we can talk to real scientists and ask them questions, and they are as long as you're polite, they will respond to you and give you useful information. So I was corresponding back and forth with this guy named Scott Kravitz from Stanford University, and I was asking, because I had my basic doubts about, well, what's a neutrino and what's an antineutrino and what's the difference? Because one of the things he was looking at was trying to see whether antineutrinos and neutrinos are Majorian particles, or meaning that they're basically the same thing. So, but my basic question is that how do they know they even have two things, whether it's a neutrino or an antineutrino? Or what do they even mean by neutrino and antineutrino? I mean, why do they even why do they even make that difference? So that was my first question, which is, why is it they call something an anti and something a neutrino? So, but so here's like a I'm sharing with you the email that I was sending to him. And so the answer that he came back with, what the difference is between neutrinos and antineutrinos, is actually based upon the products that come out. Let's see here. So what is his explanation? Okay. Because it is kind of interesting. So he's saying that we call the ones that come out of beta decay antineutrons because they balance out the electron flavor of the electron that comes out of the beta decay. So basically they're saying that it's because a normal matter electron comes out of the beta decay that that the neutrino that went in had to be anti. So that it's kind of like they're trying to balance matter and antimatterness on the equations here, which seemed a little bit arbitrary, right? That you have this kind of conservation of matter versus antimatter. So that wasn't terribly convincing to me.
Like I see Bill Lucas is on the conference, and I know Bill has quite a interest or quite a understanding of, at least in his world, about the nature of an atom and the design of an atom. Do you have any information, Bill, or any theories about the neutrino? Would you be willing to speak to that?
This is Bill Lucas. I have published a theory of elementary particles in which I define the structure of all the 96 basic elementary particles. And that is built upon the oldest work that we know of in science, which was starting with the Moses, the Hebrew lawgiver, who had a very excellent education in Pharaoh's court. And then it goes to the Indian Jains, and then it comes to the Greek natural philosophers, and they talked about the monad. And
But did they really talk about neutrinos any?
Wait a minute, let me finish. They talked about the monad. The word that we pay more attention to coming from the Greeks, not from the Moses or Indian James, is the word atom. And atom was referring to the monad, and in fact, it was uncuttable. And we didn't know as much about the monad as we would like until more recently, when we discussed that the monad was a continuous ring. We say it's a continuous ring of charge, but it's a standing wave in the electromagnetic field. So what we call charge is something we have made up. We can write an equation with something called Q or charge in it, and it seems to work to describe the data. But if the ancient philosophers were to talk to you, they would say, "What is charge?" And you'd have to say, "I don't know."
Well, the thing is about the neutrinos, though, is they're said to be, they are neutral. So
right.
I don't know how does that, I'm not sure that any of that relates to what the theory of a neutrino might be.
The electron neutrino is made of 2 monads. The muon neutrino is made of 4 monads, and the tau neutrino is made of 6 monads. And these monads, we would say, using the language of modern physics, are toroidal rings of charge E/3, because the electron consists of 3 of these. And what you have to do when you build a theory of elementary particles, say there's only one building block, the monad. Then you've got,
what is a neutrino then?
a neutrino consists, the electron neutrino consists of 2 monads. and they're a monad and an antimonad. You can have an antimonad, and the two balance out, so you don't have any mass, you don't have any net charge, you don't have any net. You do have spin, but so anyway, these characteristics you can define. So if you build all the elementary particles out of these monads, and you've got the monads cannot be created or destroyed. So they're conserved. So what you have to do in every reaction, you have to be able to show in every decay process, you have to be able to account for every monad.
So what's the difference between a neutrino and an antineutrino?
It has to do with the way the monads are put together. And
Okay,
so you can have, if you think of them as rings, I can have two rings go together where they're both going in the circulating in the same direction, or I could have them in opposite directions.
Now,
So
what about the different flavors of neutrinos? Do you believe that what's the difference between a muon neutrino and electron neutrino?
the muon neutrino has 4 monads in it, and what it is it's a pair of the basic electron neutrino is 2 monads, and then um, if you get a pair of electron neutrinos, they can combine to form a muon neutrino. And if you get 3 of them, you can combine those and get a tau neutrino. So you need a way to account, and that's what the fellow from Stanford you were talking to was trying to say, is we have these characteristics that we've measured of the elementary particles, and we've got to have to conserve all these characteristics in every interaction, decay, reaction that occurs. And so they want to try to account for all these properties that they have measured. And so that's why they have a neutrino, because they've got some things left over when say a neutron decays or something like that. They have things left over that were in the neutron, and they've got to assign those to one or more particles. And
yeah,
so,
but what the thing is, too, Bill, that they see, they can track these neutrons or these neutrinos through space. And, with the model you're describing too, that the flavor changing from one characteristic to the other, if a monad has a specific energy characteristic, and it's the smallest energy characteristic, and you have 3 monads making up an electron, and 2, 4, or 6 monads making up the neutrinos. The neutrinos seem to have the same energy level, I believe, in each of them. But you've got, if monads have a specific energy level in each of them,
well,
then you would expect 2, 4, or 6
you need to
multiplications.
see what Moses, the Indian Jains, and the Greek philosophers said about the monad. They said the monad has no measurable characteristic. It has no mass, no charge that we can measure. So they said all these characteristics are only available in monad structures. In other words, if you have a single monad, you can never detect it. Only when you have a structure. So you have a structure for the electron. It's got 3 monads, and all 3 monads have the same what we would call charge. Well, we can't measure that directly for a single. And when you do that, now you say, well, the electron has a mass. What is the mass due to if the individual monads have no mass? And the answer is it's the kinetic energy of vibration of the monads. So it depends on what that energy will be. And so you can actually calculate it. And in my work, I calculate the mass of all the known elementary particles, and I get them all to within their experimental value. And just because of the particular differences in the monad structures.
So
And
basically, a monad has no measurable characteristic. So when you combine no measurable characteristic with another no measurable characteristic, you can make a measurable characteristic of whatever kind you want.
that's right. And there's two types of kinetic or things going on in the structure. You can have vibrations and you can have rotations.
So basically, what I would say is that if monads have no measurable characteristic, and the combination of monads have no measurable characteristic or have a measurable characteristic, then you really don't need the monad no measurable characteristic monad to make anything, because you're essentially making something out of nothing then.
Well,
So,
what it is there's no free monads. There's no free monads.
okay.
So you can never measure. And so the only thing that has stability and exists long enough, you see the monads will just combine. If there's any other monads in the universe, they'll combine. And and they will form various structures. And so you can't see them. We know, for instance, from uh, the quantization of charge, because when we scatter off of a neutron or a nucleus, which has protons and neutrons in it, we can see the interior structure of protons and neutrons, and we can see that both protons and neutrons consist of three substructures, and we can measure
Okay.
the charge of those substructures, and it's not a multiple of E, the charge of the electron, it's E over 3.
Okay.
And so
Well,
we,
we're probably getting in too deep here, Will, but I mean,
if
you determined that the different types of neutrinos have 2, 4, or 6 of these monads, but the monads have no characteristics of their own by themselves.
you
So
can't measure it, you can't measure it.
right. So
But
how did you
say,
determine how
you
did you
can
determine
say
that
it has a charge,
how
but
did you determine that there's 2, 4, or 6 of them?
because you're doing the same thing that the fellow from Stanford was trying to communicate to to us, and that is that you have to account for all of the characteristics of each uh, system that is decaying. So when I have something decay to a neutrino and other things, and maybe I can make that decay go another way. And so I have two different decays, and now I need to give a consistent interpretation of that. I'm assigning, in the standard model of elementary particles, I'm assigning uh, quantum numbers and various characteristics to these pieces that are coming out in order to conserve them, because I have no other, if I don't conserve them, I can't make any progress. And so that's what they do. And so I'm doing the same thing. The only thing difference is, instead of doing strong interaction and weak interaction and that sort of thing, I've looked at the NIST data, the eight significant figures, and they show that there is no strong interaction in the nucleus and there's no weak interaction in the nucleus. There's only electromagnetic. And I've published papers on that, and it really raises everybody's eyebrows because they can't contradict it. The NIST data, which is the most accurate data, the eight significant figures for nuclear isotopes, enables you to show that there is no exception in over 3,000 nuclear isotopes that there is no strong interaction or weak interaction in the nucleus and no neutrinos. So that's what you got to deal with, and they don't want to acknowledge that.
No,
Well,
that's
so
no neutrons, right, Bill? Not no neutrinos.
No neutrons, right? Neutrons.
Not yeah. Let's not get that mixed up, because
Sorry.
neutrinos and neutrons are completely different things.
Right, right. But you see, our current theories are built on the idea that there's a strong interaction holding the protons together in the nucleus. There's a weak interaction discovering beta They're neutrons in the nucleus. And the NIST data, which has just been taken in the last 10 to 15 years, uh, shows that that is not true. But you have to use logic to get that conclusion. And what they did to protect themselves in the scientific community is they removed the role of logic. No theory can now be falsified by logic alone. And so you got to see that. And so that is that's something that, you know, they don't want to talk about in the scientific meetings. You bring that up, they'll pretend you never came. They'll take your paper out of the proceedings and all that kind of stuff because they don't want to acknowledge that, because they'd have to throw out all, you know, the theory of the atom, the theory of the nucleus, the theory of elementary particles. All those things that have to be thrown out and start over again, and they don't want to do that.
Okay, thanks, Bill. Do you think does anybody else have any knowledge or any input on what they know of neutrinos, or what they've heard of neutrinos, or any opinion of their own of neutrinos?
Yeah, anyone else have any strong opinions on neutrinos? I was going to try and share something, except my slide is kind of oriented the wrong way.
Frank, I have one comment to you.
Uh-huh.
That if you want to think about the difference between the photons and neutrinos, the basic is different. That the photons are products of neutrino. That it contains a great amount of neutrinos. That it means that the photons are, are produced from a huge number of neutrinos. That's all.
Photons are just huge number of neutrinos. Well, that would kind of go along with what I
Photons.
was
I
trying
think
to
that kind
say.
of goes. I think that kind of goes along with Hans von Leunen's theory, does it not? Does it not, Hans? Are you there?
I'm here. My particles are built out of things that I call clamps, and clamps are spherical shock fronts that occur when something that's point-like is landing on a continuum.
Yeah.
So they are reactions of the continuum on an impinging elementary particle, an impinging elementary module.
Yeah. Do you have a model then of a neutrino or in based on that, or have you delved into neutrinos at all?
I have difficulty enough to understand the electron and the quarks, and the neutrino has so little number, such a small number of these clamps that I say, well, they are strange. They are very strange in the community of elementary particles. They are much lighter. They are neutral, and all other are charged. So the electron is charged, the positron is an anti-electron, is charged, and the quarks are all charged, but the
Right.
neutrino is the only one that is not charged.
Yeah, I
And
think that's
it's very, very light. And it
yeah.
exists in 3 generations, and on their travel, they oscillate between these 3 generations. And also that is a strange, for me, it's a strange phenomenon.
Yeah, I think that's why they're still studying it. I think it's a strange phenomenon for most people in physics at this point yet.
Yeah, but all fermions have this feature as well. They also exist in 3 generations, but these 3 generations are rather stable, and the neutrinos are oscillating between these 3 generations. Maybe the other particles do as well, but that goes far more slowly.
Yes, but
Kind of why I like the definition that the Sanford lab physicist gave is of a combination of a couple of waves moving together at the different light wavelengths, and they're beating against each other, so they would change. That's about the easiest way for me to understand it, but it it's not definitive by any means.
Yeah, the neutrinos are difficult to detect, but the clamps where I'm speaking about are so small, they are very many orders of magnitude smaller than the electrons, so they are not detectable at all. Not the most sophisticated detection machine in universe can ever detect them. They are too small to be detected. You cannot observe them. But in large clouds, elementary particles are in fact consisting of a huge swarm of these clamps, and with several orders of magnitude of these clamps inside, and therefore they become, as an elementary particle, they become observable.
yes, but if you are telling that they couldn't be detected, I can't agree, because it couldn't be detected by the ideas how they want to detect it today.
Well,
Most
Not
most of most of physical reality is not detectable at all.
yeah, they're
Only
not
a
really
very,
detecting.
very tiny part of the physical reality can be detected or measured, and so if you say it cannot be detected, cannot be detected, so it doesn't exist, then most of physics doesn't exist.
Oh,
Right, because we're not really detecting them directly. Even here in the mind, they're not directly detecting them. They're detecting the effects of their encounter with atomic matter, and how in the atomic matter misbehaving when they don't expect it to. And they say, well, and then they realize that, well, they can actually send a beam in, and the misbehavior can be controlled. So they know that they're sending something in, but they're not detecting them directly. They're creating something and they're detecting something, and they can detect it, and they can recognize the source of the interaction, but they can't see them directly. You can't directly detect the neutrinos. You can only detect the photons that come from the reactions that are initiated by the neutrinos. So that, in that sense, it's kind of like what Hansa say, you know, everything we detect is basically, we detect it by an interaction of energy that occurs.
Yeah, we detect via photons, or we detect via elementary particles such as electrons. But the neutrinos are elementary particles, but they are also so small that it is very difficult to detect them. It's
detect
by
them,
accident that we detect them.
but by the system, what they want to detect, the nuclear physics is are always depending on the detect. For them, detectable is something which can produce a photon, and they are able to detect a photon by multiplier. That is all. They must change their thinking, as you say. The neutrinos are so small particles that they are not able to produce photons in atoms. So we couldn't. It's our imagination that we can detect them by the photons. How we use it in elementary physics is nonsense. You cannot detect something which cannot produce the photon, but it reacts with matter with great amount. But I say, for instance, with calorimetry, another conception, but not to detect them so as it is used in nuclear physics, that the particle constant excite the atom, and then before detect the photon in this way. Of course, they are not detected.
Yeah,
Well,
maybe
I went to
maybe the tau version of the photo of the neutrinos are detectable because they are quite heavy. There are electroneutrinos, there are muon neutrinos, and there are tau neutrinos. And the tau neutrinos are so heavy, you might be able to detect them. And since they oscillate between these three conditions, you might detect them in their tau version.
And why we have to talk about three neutrinos? There is only one neutrinos because it has a greater energy, so it means that it has greater mass. So it is another neutrino. So how they all think about it is all elementary particles about that. They are talking us that there are 100 elementary particles. It's nonsense. If all has a lifetime of 10 to minus 6 or 10 to minus 20 seconds. Where is the difference? Of course, if they have a great energy, it has a greater mass. It is just for the sense. It's just for to take a Nobel Prize that you discovered the new particles, but just simply a mass. The more greater amount of mass. Of course, if you have a proton with great energy, it has a greater mass.
Well, let's get back to the question of the different kinds. So Peter's saying that there's really only one. I mean, I was kind of doubting the difference between an antineutrino and a neutrino with my discussions here in the email with Scott Kravitz. So here, I'm not trying to be rude in my email, but I'm trying to ask him, like, how do we know what the difference between a neutrino and antineutrino is? And I've highlighted my main question here, which is, have we ever done an experiment where we generate the antineutrinos and then we do an experiment generating the neutrinos, and do the detectors see a difference? I mean, my hypothesis was that they shouldn't see any, because I think that a neutrino is exactly one thing, and if they were to shoot alleged anti-neutrino beam into their detector, they would detect exactly the same thing that would happen if they shot in what they thought was a neutrino beam. So that was my.
It might have a different spin.
Well, that was my challenge to Scott in my email here. Now, he did give me the clue that they have in fact done this experiment. It's called the T2K experiment here, which they can apparently run in both neutrino and antineutrino mode. So they've got something there that can just, using an accelerator, can arbitrarily generate either a neutrino stream or an antineutrino stream. They've got something that can split off the particles that do the interaction. And so they can control what they think are the neutrinos that come out of this thing. And well, then
they have no charge, though, so the only thing that can help to split them up is the spin. The spin can split the whole thing in two beams by an upspin and a downspin.
Yeah, but then what's upspin and what's downspin? I mean, that's clearly not. You might as well call it Mickey Mouse and Donald Duckness.
Yeah.
As far as I'm concerned, right?
So, frankly, also in photons, you have photons and antiphotons because they have various spins. In fact, standard light is going one photons, and behind the photons is going minus photons. It means that photons has also two different spins. So you can also photon calls the photons and antiphotons. Really, exactly. You can say that you have also the photons and antiphotons, because in standard beam, the photons are going one after another, and it is one spin and another spin and one spin and another spin. This is like, so you have the same. It is the same with these anti-neutrinos. It is the same like with photons. In photons, you have also different two spins of photons you have. So you can imagine it this way.
I don't know, Peter. I'm having a hard time imagining antiphotons.
Yeah, that's something I haven't heard of before.
With opposite spin to the photons before.
Well, in any case, so I asked that question to Scott, and I was expecting to find out that no one's ever done that, but no. So he pointed out this 2TK experiment. So I apologize that the slide is in the wrong orientation. I didn't have enough time to put it in the right orientation. But so this is an experiment where they're able to generate the both types of neutrinos and detect them with exactly the same detector. So in my mind, that's a perfectly fair experimental setup. So in here, they're showing, so that they've got here, it says, let me see it, where's my little pointer here? Okay, so this over here is a graph showing V mode, which is neutrino mode. And then they have the anti-V here, and that's anti-neutrino mode. So they've got these 4 different lines here, and these correspond to the 4 kinds of neutrinos that they can generate and detect in these experiments. So 2 of them are the electron neutrinos, and so those are these 2 little lines here, like orange and red. Those are the electron neutrinos. And the blue and the black line, these are the muon neutrinos. So they can detect a total of 4 different kinds of neutrinos. Well, actually 8, because there are 4 different. Well, let's see here. No, that's 4. You've got the electron and the muon, so they can detect those 2 types of things being generated. So in this down here in this graph, the V mode. So the black line is showing the detection of the neutrino species, and the blue line is showing the detection of the anti-neutrino. So even when this whole beam is in the neutrino mode, we're still detecting significant amounts of the anti-neutrino variety, and we're also detecting electrons and the anti-electrons. So this doesn't produce a pure beam of neutrinos or antineutrinos. It's always some kind of mix. So in the neutrino mode, you see that the black line is the highest.
If they occur in each other's vicinity, and that's what they say that they have, then there must be a lot of creation and annihilation of neutrinos, because then at those occurrences they change into photons. So there must be an exchange between neutrinos and photons in these processes.
I'm not sure that's true, Hans, because I don't believe that necessarily antineutrinos and neutrinos annihilate like electrons and positrons do.
How then?
That's not what I've heard. I believe they don't annihilate each other.
I never heard it, but elementary particles in general, and neutrinos are elementary particles. Elementary particles can annihilate and be created. And in fact, I have two views of the model. One is the creator's view or the storage view, and the other is the observer's view. And only the observers see creation and annihilation. What the creator sees, he can look up and down in time. He sees a zigzag of elementary particles that move up in time and down in time.
Okay.
Elementary particles can zigzag up and down in time.
Let's hear. Can I finish explaining my experiment here before we go on to that?
Okay.
So I'm just showing you here. So this is the anti-neutrino mode here. So now we see that the blue line is the largest. This is the anti-neutrino detection. So we can see that when they are in anti-neutrino mode, they detect many, many more anti-neutrinos than they did when they were in neutrino mode. So this is evidence that the neutrinos and the antineutrinos are in fact different things. So when you're in antineutrino mode, you get mostly antineutrinos. When you're in neutrino mode, you get mostly neutrinos. So I thought that was very interesting. So that basically blew away my hypothesis that you couldn't detect them separately, because apparently you can, although some of the things that you do observe is that they cannot produce a clean neutrino or antineutrino beam, that there are significant amounts of the other type always mixed in, and that like when you get down here in the I think this is the higher energies, basically they're the same, right? They're all mixed in. They're at about the same level, and they're making note of that the backgrounds are much higher in the antineutrino mode, that basically they cannot tell a difference between those in there. So, but that I would say is adequate evidence that there is a difference between antineutrinos and neutrinos, and that they can draw out these graphs shows that they can adequately detect the different types of neutrinos. Like there seems to be a difference between the electron and the muon antineutrinos. Now they do have a third graph over here. And so the way this experiment worked is that they generated their neutrinos in their experiment about 300 miles away from the big detector in Japan. And so they detected these graphs about like 300 meters from where they were when it was generated. But they also shot the same beam to the Super Kamodi detector in Japan, and they got the results that the spectra of the neutrinos looked pretty much the same as what they saw in the detectors that were near they call these the near detectors. So this graph here of the antineutrinos looks very similar to where it was generated, showing that they did indeed generate this beam, shoot it 300 miles under the Earth, and have it redetected in basically the same way as it was generated. Although my question is that if there's neutrino oscillations going on, then you'd think that the graph 300 miles later would look a little bit different than the original, and it doesn't look that much different to me. So, I mean, that would be my follow-up question, which is how much neutrino oscillation is going on here, because it looks exactly the same pretty much. But it is remarkable that they can generate a beam 300 miles away, detect it with both a near and a far detector, and come up with basically the same results.
I think the mix is the same basically when you get there, right? Is they're still dissecting or still generating all three flavors?
Well, they're generating both. They can only detect two flavors, which is the muon and the electron.
So even if they oscillated, the ones that were flavor A would become flavor B, and the ones that were flavor B would become flavor A. By the time they reached there, you would still have the same quantity of each. So that's possibly, the answer to that question. I'm not certain.
It's possible. It's like, what would they all mix into, right?
I think what they're trying to do with Fermilab and Sanford Underground Lab is they're trying to isolate and try to generate just one flavor and see, what flavor they receive when they get there.
Well, I would think if they were all mixing, that at any significant difference, they would all mix. You would detect all four types that they can detect here at equal rates, because they would eventually all mix into each other, right?
Right. Yeah. So that's why I think you'd expect the same mix when you receive them as you expected when you.
No, I wouldn't. No, that's my point. I don't think you would. You would. It's like if you take a colors blue, red, and green, and you stick them in the blender, you get like brown at the end, right? You don't get different. So you don't get three stripes of red, green, and blue in different places. They would all join together, and as they randomly mix, would all just pick, what's the most common thing to be.
Well,
So I would think it would all blur into a flat line.
It could be too that you are generating them at the same values, that your detector is just more sensitive to one than the other, and that's why the lines might not be overlapping.
It's possible. Once again, this is something that as dissidents we can go and ask. So we don't have to rely on the peanut gallery that is the dissident science community. We can actually go ask real scientists, and maybe I could send a message to the two TK guys, and maybe they would respond and say, okay,
might be worth the question.
Yeah, it's worth the question. Doesn't hurt. The worst they can do is ignore you, which is what they mostly do. But sometimes they if you ask politely, you can get some information that you can't really get by just browsing the internet or talking to people. Because I would have never known to look at this experiment, and it took a lot of digging to find this slide. Because these T2K guys, I think they're more into finding the neutrino oscillation, and they really didn't care that their experiment shows that clearly shows that neutrinos and antineutrinos are clearly different, because probably in their mind that was already a given. But in my mind, that was the main question, as to whether anyone had ever been able to even prove that. So in this entire paper, you'll never mention, hardly ever mention that, you know, we've proven that neutrinos and antineutrinos are different. But I was able to dig through the presentations, and it took me like an hour or two to dig through all the stuff that's on their website until I found this one presentation that had this one slide in it that showed what I was looking for. So, but that's dissident science is done, right? We dig through and find what we're looking for. But that was the most interesting thing I saw about neutrinos. So, in my theory of neutrinos, I'm going to have to like come up with some way to distinguish between what's the difference between a neutrino and an antineutrino. And like some people have suggested, maybe something like spin, or maybe it has something to do with orientation, or
Spin has to do with orientation.
Yeah, or it's a magnetic property, or maybe, as Cornelius has suggested, is maybe it's an interaction of phases.
No.
It could be any of those things. So that's a matter of speculation.
The properties of a neutrino are its mass, its speed, its spin, and its electric charge, but the electric charge is 0. And more,
Well, I would say that
more
a neutrino
properties
doesn't have
than
things like, doesn't have electric charge and stuff like that, because it's clearly neutral. So
the mass is coming out in the generation. A muon neutrino is heavier than an electron neutrino, and a tau neutrino is still much heavier than the muon neutrino. So
no,
that's
actually, I think that
in the generation.
Experimentally, that still hasn't been established. I mean, I feel that neutrinos, if they had any mass, they would have been able to, you know, the example given is a supernova, and they saw the neutrinos come in at basically the same time as the photons, and that's strongly indicating that neutrinos have no mass.
Yeah, I think they're just indicating it has an energy level. They originally speculated that it didn't have any mass, and now because of the oscillation characteristic, they're speculating that it might have some mass, but I haven't heard anything where they have said that one is heavier than the other as far as a mass type characteristic. Unless that's my understanding at this point. I haven't heard anybody around here in this physicist group that's involved with this experiment say that they've determined there's a mass difference between the three.
You can get figures about the mass of the tau neutrino and the mass of the muon, the expected mass, not but they have figures that about their expectation of what this mass will be.
Well, that's why they're doing all these very expensive experiments to figure out, I don't know, it's like there's a theta 1,3 parameter or something, which is determining something called a mixing angle, whatever the heck that is. And when they figure that out, then they'll be able to, because the mass is a theoretical a consideration, that because the only way they can switch flavors is if they have some kind of mass. So it's critically important for them to figure out at what rate these things are switching so that they can figure out what that mass could possibly be. Now, me personally, since I think that neutrinos are just an EM wave phenomenon, very short, that neutrinos would absolutely have zero mass. They are a wave phenomenon, therefore have zero mass. So, and I would say that that the neutrinos, the flavors, that's more a detection difference, that you just have detectors which are more sensitive to the various ways that neutrinos can interact with matter. If you have one which is sufficiently sensitive, then you will see all of the neutrinos like from the sun. But if you have a very limited ability due to your experimental setup, then you'll only see like a third. And that's not because 2/3 are missing, it's because your experiment is simply insensitive to the other 2/3 of the neutrinos coming in. At least that would be my opinion on that.
Oh, I don't. I disagree. frankly, because it is the same question like with the mass of photon. Of course, photon has a mass, and proclaiming that photon has no mass is just wish of relativity, and it's just wish of power structures. Doesn't that mean that space is not free? But photon has standard mass, which is different, which is depending on the energy of photon, and the greater energy of photon has, the greater mass is the greater mass photon is spin products of cool compression of ether, or you may think also of cool compression of neutrinos. It is for me, it's very similar, and photon has standard mass, which is by the standard relation for photon. For me also the neutrino has those two mass also. So as the
Well,
photon has its very mass. Okay.
any,
I don't think photons
any
have any mass. That's pretty clear.
no, anything that moves the speed of light can't have mass, or it would have infinite mass according to E equals according to increase in mass with velocity. And photons have energy, and that energy can be equivalent to, compared to a mass that has energy also. You can have gravitational mass, a mass that, but the thing about a photon is, if you stop it, if it's static, it's no longer a photon and no longer exists. If you stop mass, mass can stay in a particular space, spot in space, and mass is a form of energy, just like a photon is a form of energy.
Well,
But
how
you can't have energy moving at the speed of light and still have mass.
so the same way as a wave in water is moving, and or wheels or curls in water, the mass is the compression of the more amount of this water when you have a wheel or curl in water. It is the same principle. I don't see any.
No, because in the case of water, the wave is moving and the energy is moving through the wave, but
I
the
am not
mass of
talking
the water itself is not moving. It's moving perpendicular to the direction of motion, but
if you
the wave
stop
is transforming the energy.
if you stop the wave in water, or better say the wheel or toroid in water, so it disappears, of course, the same way.
If you stop the wave in water, then you've got an electron. If you've got a circling around a circular direction, then you can have the mass of that particular location, because now you have stopped it. But photons don't stop. If you stop a photon, you've basically got an electron, because it's traveling around in a circle now.
You can stop a wave in the water. You can also not stop the wave in the water. If you stop it, so the wave will disappear. There is no difference. And the mass mean the more compression of mass of wave, or better say of toroid in water, the more you compress the water, the more mass is there. And with photon is the same. You have some ether, when you produce the photon, you compress it, and when the length of photon is 100 meters, so it's a huge volume, and even if you compress the photon to 10 minus 7 to visual photons, or 10 minus 5 to 15, you compress a very much amount of matter, and that is the mass of the photon, and we have standard relation for it.
Well, we'll just have to agree to disagree on that, in that interpretation, I think, at this point, and move on.
Planck constant divided the wave of photon is the mass of photon. The standard relation for it. MC equals Planck constant divided wavelength of photon is the mass of the photon. MC equals h divided by lambda. And if the lambda is smaller and smaller, so the mass is rising. There is a linear relation between mass and wavelength of photon. MC equals half divided by lambda. If you
That's just describing the mass equivalence of a photon. It's not not telling you that there is mass, but it's a mathematical formula equating the amount of energy in a mass to the amount of energy in a certain length of a photon. It's not really a physical commonality. And that's my opinion on it. And I'm going to just leave it at that so we can move on or somebody else can discuss it.
but the same equation is also for the mass of ordinary mass. There is no difference. It's just a wish of relativity that there is no that mass of photon has that the photon has no mass. It is just wish because then you can make in a standard equation for energy you can make a cross against the term of rest energy, and then you can work with it. That is the reason why they are telling that the mass of proton, but it's not there.
Well, I would agree that that's more like a mass equivalence. Although I don't believe that equivalence makes any sense. So if you can always convert like the energy of a gamma ray into a certain amount of mass through E equals mc squared. But I find that an extreme violence to logic. I'll put it that way.
Photon have no mass, so if you produce the proton, antiproton, so from what this is going from? So photon has to have a mass because they can produce a real matter. They can produce a protons. So you say that photon has no mass. So when at the case of particle creation from what they are producing, if the photon has no matter, but from high energy you can produce standards for photon produce.
Anyone who wants to argue that would have to explain how a photon converts into a positron and electron.
Oh, that's
How
done.
does that happen?
It's done. It's done during particle creation and during particle annihilation. There, the exchange take part.
That doesn't tell me how the exchange happens.
Yeah.
What is the mechanism by which that exchange happens?
In my model, there exists a category of very tiny, super tiny particles. I call them clamps and I call them warps. And a clamp is carrying a standard bit of mass. And a warp is carrying a standard bit of energy. And what happens on those occasions is that you exchange warps against clamps or clamps against warps. And that happens at particle creation or particle annihilation. And it also
But frankly, it has another simple relation. If from photon, if you have a photon higher than high energy photon, and your question is how is produced the for instance proton antiproton particle from photon. It's simple. There is no produce. It is there, but you just stop the photon, and in that in a moment the proton begin to exist because the gravitational field simply arises around the proton, and there is no creation. It is simply if you have a 10 to minus 23 gamma radiation photon, so it's in fact is the proton is there. But if you stop it, that photon for the creation of proton, antiproton particle you need 10 to minus 23 frequency of gamma radiation. And the proton is there, but if you stop it, so it is fixed, and you see that, okay, it is in a rest state. So this is how, and it is the same with electron and anti-electron. If you, for creation of electron, anti-electron, you need 10 to minus 15 frequency of photon radiation or gamma radiation or X radiation, and the electron is there. And the electron and anti-electron means that the photons which are going one after another have another spin, and in fact from one it creates a proton, and from the opposite spin of photon which is going in line beam is producing the anti-proton or anti-electron or what you want.
I mean, that's possible, but it's pretty arbitrary argument. You're just saying that the photon, already basically has a positron electron in it. When it stops, then the positron electron come out.
I don't think you're
Basically.
actually, I don't think you're going to actually find a situation where a photon is going to change to an electron or positron unless it encounters a mass to begin with, and the energy in the photon or a positron can be converted to an electron positron once it encounters a bit of mass, but it has to be absorbed by the mass, and then you can convert that energy into additional mass in that mass structure, and that energy takes the form of a charge, which then gives you the electron or positron or proton.
But that seems rather complicated. I mean,
Well, it's not,
my own take on it is much simpler, which is I think that the photon is just a wave,
No, it
and
isn't.
that's energy, and
Yeah,
that the positron and the electron already existed in space.
a wave
as-
cannot
as
do what
ether.
a photon does. So a photon is never a wave. A photon can travel a billion light years and still exist and have sufficient energy to trigger a detector. That's what a wave never can do. A wave.
Well, I think previously we went in our discussion of what a photon is. I mean, I think we were splitting definitions there,
But
and that we were just talking about your shock wave, which is what I would consider the photon to be.
Let me explain what a photon is. A photon is a string of these warps. Warps are one-dimensional.
Well, I don't think that they need to be things called warps, because I prefer to think that what we have here is in fact a wave phenomenon like sound. It doesn't
isn't.
actually involve any. I mean, I'm just explaining what I think it is. Okay, I think that the simplest explanation is that the photon is in fact a wave similar to a sound wave. It's just a compression wave, except it's a very, very small, short wave. And what it does is that it hits